Global warming in excess of 2 degrees Celsius above pre-industrial temperatures has been widely recognised as being dangerous. However, staying below this would require annual emissions reductions of 30 to 85% relative to today by 2050. The lack of progress in reducing carbon emissions over preceding decades has prompted interest in geoengineering strategies, large-scale human interventions in the Earth's climate system. Enhanced silicate weathering, a soft geoengineering option, will be the focus of this short film. The reaction of CO2 and water with silicate minerals and rocks releases positively charged cations such as magnesium and calcium, as well as bicarbonate ions. These ions are then transported to the ocean, where they are incorporated into the shells and skeletons of marine organisms through carbonate precipitation. Upon death, the carbonate material sinks to the sea floor, where it is buried, removing carbon dioxide from the atmosphere. Enhanced weathering can take the form of CO2 injections into silicate rocks and the reaction of CO2 with minerals in pressure reactors, but here we will focus on the most cost-effective and energy-efficient option, the terrestrial spreading of silicate minerals. The silicate minerals could be derived via direct extraction, but also to a less extent from industrial byproducts such as steel slag and fuel ash. Arable land, particularly in the humid tropics, will offer the most suitable environments for applications, as warm temperatures, high moisture levels and accessibility will be key prerequisites for the success of any enhanced weathering scheme. At a global scale, Streffler et al. Estimated that 3 gigatons of basalt, just under half of global coal production, would need to be spread each year to sequester 1 gigaton of carbon, or approximately 10% of annual carbon emissions. However, a number of uncertainties are concealed within such estimations. Such a value could be deemed an upper limit, as it didn't consider resistance or opposition by existing landowners to the implementation of enhanced weathering. Additionally, the carbon sequestration potential of enhanced weathering may be partially offset by between 5 and 30% because of emissions from mining, processing and transportation. The primary source of uncertainty in these emissions estimates is from the comminution requirements, as applying finer grade particles will increase weathering rates but will also drive higher energy usage during rock grinding. Enhanced silicate weathering may also produce a range of co-benefits, 2 of which will be discussed in greater detail here. The first co-benefit relates to diatoms, single-celled algae, which play a major role in the export of organic carbon to the deep ocean. As diatoms are believed to be silicon limited in large parts of the world's oceans, a greater terrestrial flux of dissolved silicon from enhanced weathering into the oceans may augment diatom productivity and the transport of organic matter to depth. However, abiotic factors such as ion concentrations, light availability, and temperature may heavily modulate the elasticity of diatom productivity in response to silicon fluxes in different oceanic regions. In addition, river damming on many of the world's largest rivers may prevent large proportions of the silicon from reaching the ocean in the first place. The second plausible co-benefit relates to the consumption of free protons in the soil by bicarbonate ions formed in silicate weathering. This raises the alkalinity of the soil and the bioavailability of plant nutrients, bolstering plant growth and the storage of carbon in soils and plant biomass. The plants themselves will then promote weathering further through the release of CO2 into the soil from respiring roots and the direct dissolution of minerals by organic acids. Undertaking enhanced weathering at a geoengineering scale would necessitate major expansions in the contemporary global mining industry and the upgrading of regional transport infrastructures. For example, Edwards et al. Estimated that applying 5 kilograms per meter per year over 6.7 million kilometers squared of tropical croplands would require 33 petagrams of rock per year, which is between 2 and 5 times greater than current global silicate production. The remote nature of extensive basalt outcrops, such as those in Siberia and Ethiopia, together with the limited road accessibility in some agricultural areas, may hamper the widespread deployment and economic viability of enhanced silicate weathering in tropical regions. Enhanced silicate weathering may also generate a range of both deliberate and inadvertent environmental impacts. Upscaling present-day global mining operations will entail destructive practices such as mountaintop removal and deforestation. The discharge of elevated sediment loads from adjoining fields into rivers and coastal waters could also have adverse consequences for associated ecosystems due to higher turbidity levels.
To conclude, enhanced silicate weathering should not be implemented until greater clarity about its effectiveness, logistical feasibility, and environmental side effects have been obtained.